Good morning. Hope you all are doing well. So last time we talked about files, and then before that we talked about vectors. And when we were talking about vectors, we hit on the general idea that a vector was a dynamic array. And we saw, why it was so powerful in terms of the different kinds of things that you could do. In particular, things like resizing the vector at any point in time. So we saw that with things like, for example, pushback and popback, we can dynamically change the size in terms of growing or shrinking the vector structure while the program is running. And we kind of, loosely said at the time that it was based on pointers and this idea of dynamic memory allocation, which is when you're declaring memory on a dynamic basis while the program is running. And so in chapter 9, we're going to learn about pointers. And at the end of the chapter, we'll talk about what's called dynamic memory allocation. And those things really are the basis of the entire vector class, right? In terms of what really makes it work the way that it does. Because one of the things that we hit on was the issue of size versus capacity, right? When we talked about vectors. And the idea that we have, as we saw, there's functions that you can use to get both, right? So you can call the size function to get the current size of the vector. You can call the capacity function to get the current capacity. And the idea was that when the size reaches the capacity, you have to handle that situation. And one way, certainly in general, would be to, like let's say size is 10 and capacity is 10. One way would be to simply add 1 to the capacity. But then we said that the downside there was that you'd have many more times where you have to go through the process of recreating the vector of a larger size. And so we also talked about the idea behind doubling the capacity. And that was going to reduce the number of times that you have to go through that whole process of recreating the vector somewhere else of the larger size, right? And then copying the elements from the old location over to the new location. And that was a key point of it, right? Was that at some point you're going to have to redeclare the vector of the new size. And so what that really involves is pointers. So we want to remember that vectors really are arrays, but they're arrays that are being dealt with on a dynamic basis. And we'll see later how that's going to work with the keywords new and delete. But it's based on that, and it's based on pointers, because one of the things that we're going to see certainly is that in C++, the only way to really do dynamic memory allocation is with the help of a pointer. And so that's a big reason of why pointers are so important. And to start with, though, we want to think about, fundamentally what really is the idea behind a pointer. And what we're going to see is that a pointer is a variable just like anything else, right? But what it's really being used for is to indirectly refer to some other variable in the program. And we've seen something similar to it already, right? When we talked about things like pass by reference. We know, for example, that when we use that ampersand in the function prototype and function header, that the reference variable is able to work with the original variable, for example, back in main. And we'll eventually look at that same kind of issue, but in terms of pointers. And so when we're working with pointers, really the key word there is the word indirection. So that's the term that we'll see come up a lot, because we're indirectly working with some other variable through the pointer. And another term that we'll see is also the term dereferencing. But a pointer is just a variable like anything else, but what it's storing, as we'll see, is the memory address of another variable. And we've talked, throughout the chapters and the different examples we looked at, we've certainly talked about the idea of memory addresses before when we've done things like looked at our memory diagrams. And we know, for example, that when we're talking about an array, that the name of the array refers to the starting address of the array. And in fact, throughout this chapter, we'll look at the close correspondence between arrays and pointers. But that's what a pointer is storing, right? Is it's just storing a memory address, but the memory address of some other variable that we have in our program. We'll also see that just like any other variable declaration, that a pointer is going to have a type. So one of the things that we indicate when we declare a pointer variable is what type of data value is it going to be pointing at? For example, is it going to be pointing at an integer, or is it maybe going to be pointing at a double or a string? And you know, some of these topics you certainly will see again in the 260 class, right? The assembly class. Because, you know, in C++, we work with the type system. We think in terms of things like integers and strings and characters. At the assembly level, we think more in terms of size, right? How many bytes of data does this data take up? And so you'll see how we'll think about these kind of things in a very different way when you're working at that low of a level. But in terms of pointers in C++, we still need to think about the issue of type. Because as we've mentioned before, different types can take up different amounts of memory. With, you know, integer, for example, usually taking up 4 bytes, double might take up 8 bytes, type char 1 byte, and so on and so forth. So we still will need to be specific in that sense when we declare a pointer variable. So we'll specify always what type of data value is the pointer pointing at. And we'll be using the star or asterisk operator really in 2 different ways, as we'll see. But one way that we use it with pointers is to declare a pointer. And we'll see that the ampersand, right, which we're familiar with that from things like pass by reference. But we'll see that operator come up in a different way, right? Because in general in C++, some operators have different meanings depending upon the context in which you're using them. So we've seen the ampersand used with pass by reference, and we'll see it used in a different way here in terms of pointers. Okay, so that's the basic idea. And we say things a lot like, for example, we've declared a pointer, maybe we've named it a PTR or just short for pointer. And maybe we've made PTR point at some variable X, where X is maybe just an integer type variable. And whenever we say that, we have a pointer pointing at some variable, what we also really mean is that it's storing the memory address of that variable. So that's where that idea of indirection comes from. So as we'll see, when we establish that kind of connection between the pointer variable and the thing that it's going to be pointing at, then we're able to work with that variable indirectly through the pointer. So if PTR, which is our pointer variable, is pointing at X, then we can do things like, for example, if we wanted to do a cout type statement maybe and print out the value of X, we could do that indirectly through the pointer PTR. If we wanted to change X's value from, for example, maybe it's initially 5 and we want to change X to 99, we can also do that kind of statement with the pointer PTR as well. And so the whole idea, right, is if we've established this connection between PTR and X, then anything that we could do with X directly, we could also do in an indirect way with PTR. And it comes down to really what we said on this highlighted line here. The reason why that's possible, as we'll see, is because of the fact that that's what PTR is storing, is the memory address of this other variable X. Okay. Now, the first thing that we'll look at here is how do you declare a pointer variable? And we're going to see that it involves the star operator, and we'll see actually that the star operator really has two different usages with pointers. So you're familiar with it in terms of the multiplication operator, but we'll see that it has two usages with pointers, and one of those usages is to declare a new pointer variable. And the other, which we'll see in a bit here, is what's called dereferencing the pointer. And now another one is the ampersand, which we've seen that used before in terms of pass by reference. We'll see it used here in a different way. So the ampersand operator can also be used to get the address of a variable. And that's a key part of this, because we said up here, right on this bolded line, that the pointer, in terms of what it's storing, is it's storing the address of some other variable. And so we have to have a way in general of course, getting that information. And we can do that with the help of the ampersand operator. And so using those two operators together, we can now think about how to start setting up these pointer variables. And so this would be one way of initializing that pointer, which we're calling PTR. So in the example here, we've created some integer variables, X and Y, where X has the value 5 and Y has the value 6. And then the goal on this line was to make PTR, this new pointer variable PTR, but we wanted to make it point at X, which means that we want it to also store the address of X. And so what we did here was we used both of these two operators together, meaning the star along with the ampersand. The idea being that the star here on the left is needed to make it a pointer, right? Because if we don't have the star and we just said something like in PTR, then that would mean that PTR would be treated as just a regular integer type variable, meaning it'd be the same type as things like X and Y. But by including the star there, we're now saying that, you know, PTR is not an integer, but it is a pointer to an integer. So that's the type here, right? The type really is all of this together, meaning int star or pointer to an integer. So that's the type of PTR. And then the value that it's storing, right, which is coming from the right-hand side of the equal, is the address of X, right? The memory address of X. Because that's exactly what we want to have happen when this statement has executed, is we want X's memory address to be stored in PTR's location in memory. And so, of course, that also means that if we, you know, for example, forgot to put the star there, then the declaration would not even be valid, right? Because we can't try to do something like take the address of X and then store that in another integer type variable, right? We can only store it in a pointer. So we definitely are going to be using the star on the left-hand side here. But what about the right-hand side, right? Well, we need the ampersand as well, because that's how we're going to actually get the address of X. If we didn't have the ampersand there, then that would be just referring to X itself, meaning it'd be referring to the value of X, which would also be invalid. Because we have to think about the strict typing system here. Since the type is int star, that means we can only store address and not a value. So trying to do something like int star PTR equals just X without the ampersand, that would also be an example of something that's invalid because we can't store a value in a pointer variable, right? We have to store address. So in this case, we're going to need both of those two things together to make this declaration work. So that's going to start us off by forming that connection here, where PTR is going to be pointing at X. And then the idea is from there, we can start to use PTR to do things with X, whether it's a read type operation, like maybe a cout statement, or perhaps a write type operation where you're going to actually be changing X's value. Now, one thing that we can think about before we start going a little bit further with this is we can step back and think about the memory situation, because we have this important realization that when we say things like PTR is pointing at X, what we really mean is that PTR is storing the memory address of X, because that's what's going to make this whole concept of indirection possible. And so let's look at a sample memory diagram here to get us started. And we'll look at how this memory diagram is going to change as we add some more statements along the way. And because we really mean that we have something like this going on. And again, we're just choosing, arbitrary addresses here to show the point. But here in this diagram, we're saying that X, right, or X's value is stored at address 20. Y's value is stored at address 32. And then the pointer, right, because the pointer is just a variable like anything else. So the pointer itself has to have an area of memory for what it's storing, which in this case is a memory address. So the idea then is that PTR is at address 72 in this case, and what it's storing is the address that corresponds to the X variable, which would be address 20. So that's why, in terms of our diagram here, for PTR, we have an address in both columns of our memory diagram, because the address under the address column would be where PTR itself is in memory. So PTR resides at address 72. And then what it's storing just happens to be the address of some other variable, right? So it's storing address 20. And if we're working in a 32-bit mode, then the memory address itself that's being stored here will also take up 4 bytes of memory, so meaning the same size as an integer value. So just like we said before, that when we think about integers in memory, that we know that they really take up 4 consecutive slots. So it'd be the same idea also for the for the pointer. So meaning that it's, in particular, what it's storing is a memory address, and it's a 32-bit memory address. So in that case, if the pointer itself starts at address 72, that just means that it goes up to 73, address 73, 74, and 75, right? So those 4 bytes in memory to store that address. So this would be then our memory diagram based on what we've done so far. And again, all we've done so far really is we've declared a couple of integer variables, x and y, and then we declared the pointer variable, which we have made point at x. But this would be what our memory diagram looks like. And based on this, now we can start to think about, well, how are we going to work with x indirectly through the pointer PTR? And it goes back to what we started outlining at the beginning here, was that there was going to actually be two different ways in which we'll be using that star operator with pointers. And we saw an example of the first one here with declaring a pointer variable, because that was exactly what we were doing on this line. But the other one is refers to this term which we call dereferencing. And in fact, indirection and dereferencing, those are two big terms that come up with pointers. But really, when we talk about this idea of dereferencing the pointer, that just really means that we're going to work with the thing that the pointer points at. So PTR currently points at x, and as we saw from the memory diagram, that just really means that PTR stores the address of the x variable. And so then if we dereference the pointer, that just means that we're now going to be able to do things with the x variable, but we're going to be doing it through PTR. And that could be any type of normal operation that we could do, like a cout, a cin, and so on and so forth. And so that once again will involve that star operator. And so the idea is that in terms of which of these two meanings we're talking about, declaring or dereferencing, has to do with when you're using the star operator. So here we know that this is a declaration because the type is also involved, right? Because we're saying in star PTR. So that means that we're declaring a pointer variable for the first time rather than referring to an existing pointer and dereferencing it. So in that sense, right, the first time that we set up the pointer, which is also where we refer to the type, because we have to always declare the type when we declare a pointer, that's a declaration. But now if we, at some point later in the program, put that star in front of PTR, now it has this different meaning of dereferencing. So that'd be an example of how we can do things like print out X's value. So all we need to do here is place that star in front of PTR. And since the pointer's already been declared, we know that in this context, it means dereferencing rather than declaring a brand new pointer variable. But again, we want to think about what's really happening here. So the statement itself is just cout star PTR, and the goal of that is to print out X's value, which in this case is 5. But we can think about what's really going on there. And because one thing that you can also think about is, what would happen if we did a cout statement like that, but we forgot the star. So in other words, if we just had done cout PTR. And that'll help us also see the difference between a statement like this versus a statement like this, where we also have the the star showing up. And because when we think about a statement first here, like cout PTR, well, in general, we know that when we do a cout statement with the name of a variable, what it does is it prints out the value of that variable. And that also applies to a pointer. So even with pointers, we still think in terms of address versus value. We can talk about the address of the pointer itself, where the pointer itself is stored in memory. We can also talk about the value. And that also is an address because that's the address of what the pointer is pointing at. In particular, we saw here that the address of the pointer PTR itself was address 72, in the same way that the address of Y, for example, is address 32, or the address of X is address 20. But the value, in terms of the data value that PTR is storing, well, it's the address 20. So it follows then, if we were to just do a statement like this, meaning the one that's highlighted here, cout PTR, then what it's going to print out is a memory address, right? It's going to print out the address 20. And as we'll see when we run this, it's going to print it out in what's called hexadecimal, which you talk about binary and hexadecimal in the 260 class. But so we don't really get into the details of that here, but that's how it's going to display it. But that's what this is going to print out. So because, and again, that's just in the same way that we know that if we do cout X directly, right, that's going to certainly print out 5 because 5 is the value of X. Same idea applies here to the pointer. So the value of PTR is address 20, which is why it's going to print that out. And then we can think about, what kind of thing is really going on here. So what is really happening with a statement like cout PTR? Well, cout or cout star PTR. So cout without the star is printing out the address. What's really happening here in effect is that, we're almost thinking about this kind of like a lookup table. Because we know that if we just put PTR itself, right, that would give you the value in terms of what PTR is storing. But of course, that's not what we want to print out if we put the star in front, right? Because if we put the star in front, then we actually want to print out X's value. And so PTR by itself would return address 20. But the idea is now we have that star there as well. So in effect, right, we end up with a statement that's going to look like cout star address 20, which means that we're going to go to address 20 in memory and return the value that's there, which is the value 5. And so we end up with a statement like that ultimately in the end, right? Where we're going to print out the value 5. So in terms of the code that we wrote, we would just be writing cout star PTR here. But then we have that realization that PTR itself just refers to address 20 in the same way that X would refer to its value, which is 5. So then we ended up with a statement like this, right? Where you have the star and then address 20, which means really go to address 20 in memory, and then we're going to grab the value that's there and return that, which is the value 5. So in the end, we really end up with a statement like this, where we're going to just, of course, cout the value of X, or the value 5 there. And it's also a similar idea if we want to do things like change the value of X. So star PTR equals 99, for example. And we can think about, similar to what we did up here, how this is working as well, because we said that it really was kind of like a lookup table, but it's helpful to relate this back to regular that. And so we said that with the statement like the cout statement here, that PTR was really going to resolve to what it was storing, right? Because we related that to something like cout X, which we know that, of course, that's just going to resolve to the value of X. But now we have a little bit of a different situation here, where we're doing this in terms of an assignment statement, and PTR is on the left-hand side here. But when you think about a statement, we're using a variable like X equals value. Well, in that case, when you refer to X, then you would be talking about the address of X, right? So when we say X equals 5, of course, we know that that means that the value 5 is going to go into X's location in memory. And we're doing the same kind of thing here, but through the pointer PTR. And if we're talking about our example here, the address of Y was address 32. So meaning that, assuming we're following our diagram here, then this means address 32 equals 27. So in other words, we know that with regular variables, whether it's referring to the value of the address depends on how you use it, right? So with the cout statement like cout y, we know that there it's going to refer to the value that y is storing. Whereas when we use a statement like this, where y is on the left-hand side of the equal, in that case, y refers to its address, right? In the sense of taking the value 27 and then storing it at that location in memory. And it works the same way with the pointer as well. So here we had a statement where the name of the pointer was showing up on the left-hand side, but we also had the star there because the goal was to change x's value, but to do it indirectly through the pointer PTR. So in this case, if we go back up to our memory diagram here, well, we know that what PTR is storing is address 20 because that was X's address, but we can also talk about where the pointer itself is in memory, right? Which in this case was address 72. So we can think about it like in this kind of sense. So when the name of the pointer shows up on the left-hand side here, similar to how this works with the regular variable, we know that that is referring to the address of the pointer itself. And so we end up really with the statement like this, right? So star address 72, but then when we do reference it, we're going to get the value, which is address 20, because that's really what we ultimately want here is we want to eventually get to a point where what we're going to end up with on the left-hand side of the assignment statement is the address of the X variable, which is address 20. So we have to ultimately get that as the value on the left-hand side. And that's exactly what's going to happen when we apply the star operator to the address of the pointer itself, right? So star address 72 in this case is just going to return the value that's there, which is address 20, right? Because that's exactly what we had established here in the table. So we apply that dereferencing operator to address 72. That just returns address 20. And that's where we want to store the value on the right-hand side of the assignment statement. And so we're going to end up with that. And so the end result of that is that now we have stored, in this case, the value 99 at X's location in memory. So now that we've made a change, right, we can go ahead and look at our updated diagram here. And so everything is the same except for the fact that now this is going to be 99. So the 5 is now gone, and now we have 99. And so that gives us an idea now of how to start using these pointers, right? Because we just used PTR to work with X, first to print its value out, and then to change it. Now, the other thing is we can also talk about changing the pointer itself, meaning making it point at something else. And now we saw that whenever you wanted to change the thing that it was pointing at, so PTR points at X, and then we want to change X's value, we did that with dereferencing, right, with the star. But another thing that we can talk about, for example, is maybe now we want to make PTR point at Y instead of X. And how are we going to do that? Because one thing that you could think about is if that's going to once again involve the star operator or the dereferencing operator. Because we saw that it was involved whenever we wanted to do anything with the X variable. So when we wanted to change X's value, such as with the statement star PTR equals 99, we use the star there for dereferencing. When we wanted to, earlier when we wanted to print out X's value, we use the star there. But now we're talking about actually changing the pointer itself, because those are both things that are possible. Meaning we can, yes, we can change the thing that the pointer is pointing at, but we can also make the pointer point at another variable, right? So in other words, we don't have to keep our pointer PTR, we don't have to keep it always pointing at X. We could point it at another variable, such as the Y variable, but we can think about what that statement's going to look like. So we've seen already what it involves in terms of changing the thing that you're pointing at. Now we're going to make PTR point at Y. But we've talked about the different operators. So putting this all together, we've talked about the star and how that is used for dereferencing. We've also talked about the ampersand and how that is used to get the address. And so here, now we want to have PTR point at Y instead of pointing at X. And we know that if we want to get the address of Y, then we can do that with the ampersand. So that's something that we'll think about using here. And then we can also think about whether we're going to be using that star or not. Now, if we do a statement like this, then, so we're basically trying to use both of them here, with star and ampersand. And now, when we originally declared the pointer variable, we did do that. Meaning up here, when we originally declared the pointer, we did use both. But here we mean something very different, right? We're not talking about declaring a new pointer. We're talking about actually working with a pointer that we've already established. And we can think about first what would happen if we did use the star, because it's the same as what came up in the previous example, which means that we would be trying to dereference the pointer. And because we saw, for example, before that if we did star PTR equals 99, then that was going to take the value 99 and place it in X, because when you dereference the pointer, that's what you got was the location of X. Here, we're wanting to make the pointer point at Y instead, though. And so really, we have to think about what the goal is, because now what we're really wanting to change in terms of our diagram here is right now PTR is storing address 20, which is the address of X. And if we do this correctly, then what's going to end up happening is we're going to be storing address 32 here, because that's what it's going to take to make PTR point at Y instead of pointing at X. So we're going to end up with a new memory diagram where this is going to be address 32 instead of address 20. Now, we know that if you use the star on the left-hand side, then that'd be referring to what the pointer is currently storing, right? Because when we said star PTR equals, for example, 99, we said that really, in the end, evaluated to address 20 on the left equals 99. Because address 20 was in the address of X, which is what PTR was storing. On the other hand, if we don't have the star, then it's going to be on the left-hand side, it's going to be referring to the address of the pointer itself, which is address 72. And that's what we actually need to refer to. Because when we talk about storing Y's address in PTR, we mean that really we need to store that here at this location memory, meaning address 72. So in this case, we're going to use the ampersand, but not the star, since the goal is to actually change what the pointer is pointing at. So we're just going to say PTR equals ampersand Y, right? Or PTR equals address of Y. And so we're starting to see some of the major distinctions here, because whenever we say a statement like star PTR equals, we know that we're really talking about changing the thing that the pointer points at. Whereas when we don't have the star in front, meaning with a statement like this, then we're talking about changing the pointer itself, meaning PTR equals, in this case, the address of Y. So when we look at our memory diagram here, what's going to change, we already changed X's value previously, but what's going to change from here to the next diagram is that it's going to say now address 32 here instead of address 20. Okay. And so now if we repeat some of those statements that we did before, where we did things like cout star PTR or star PTR equals new value, now the difference is we would be working with Y instead of X. So the same things that we mentioned before apply here, but just now the difference is that now it's storing, the pointer storing address 32, meaning it's pointing at Y. So now if we do things like the cout statement, right, that's going to be printing out Y's value. Or if we now do a statement like this, now it's going to be, you know, storing that in Y's location instead of X's location. And it's really the same for the same reason that we mentioned before, that when you apply that star operator and do the dereferencing, that you really want to think of it as a, essentially like a lookup table. So when we do the cout statement here, this really we said was star and then address 32, which means we're just going to go there and return the value that's there, which is the value 6. Or when we do a statement like this, where we have the star PTR on the left-hand side, that PTR would refer to the address of PTR itself, and then we dereference it, which would give us address 32. And so that's why this is ultimately going to be storing the value on the right-hand side at Y's location in memory. Yeah, good question. A big reason for pointers, as we'll see, is going to be when we want to do things on a dynamic basis. Because when we talked about the vector class, we kind of hinted that really a lot of what it involved was pointers. Because when you think about things like the pushback function, which we know that you can use that to, for example, take an empty vector and add new elements one by one. But what that's really involving is pointers, along with what's called dynamic memory allocation. Because really what's happening there in terms of the vector class and what makes all that possible is we're really just going through the process of declaring the vector potentially many times. So whenever the size of the vector reaches the capacity, at that point we have to redeclare it with a larger size. So for example, the vector is currently size 10, capacity is also 10, but we want to still add more additional elements to the vector. Maybe we want to, you know, add 10 more elements. And so what's going to happen is we're eventually going to reach that capacity, and we're going to have to redeclare it somewhere else in memory of a larger size, right? Because whenever we declare, you know, a vector or an array type structure, we have to allocate enough memory in one block to store the entire thing, because we know that in order for an array or vector to have that random access where you can go to any location in the structure without having to visit the previous locations, in order for that to work, right, the elements have to be stored back to back. And so when we reach capacity, we have to declare it of a larger size, and that is going to involve in part a pointer. Because one of the things that we're going to see at the end of this chapter is how to do what's called dynamic memory allocation. So we'll talk about the new and delete operators. And the idea is that when you use the new operator, and you can use it to do things like declare a dynamic array, but when you use it, what it's returning is a memory address. And the only way to really take advantage of that and use it is with a pointer. So one of the big benefits of this is to be able to do things on a dynamic basis. Because really that entire vector class is based on those concepts, right? You are working with ultimately an array, right? We know that arrays are the basis of the vector class, but aside from an array, it's also involving things like pointers and this idea of dynamic memory allocation. So the vector fills up, you still want to add more elements. So now we're going to dynamically create a new array of a larger size, right, somewhere else in memory. And then we're going to copy the elements from the old array
to the new array, and then from there we can add the new elements and so on and so forth, and then delete the old array. So all of that involves pointers, because we'll see that you have to use a pointer to really take full advantage of dynamic memory allocation. So that's one of the big reasons for this. Yes. A good question. So now we're starting to see some of the basics here. And we do have to make those distinctions, such as, when to use the star versus when to not use the star. And we've looked at examples of things like, what's going to happen if we do a cout statement, or what's going to happen if we do an assignment statement with the star on the left-hand side. And so now we'll look at some code examples and tie all this together here.